we have already seen two properties that allow us to compute limits. But let's see a very important one. So this is an important one, so let's call it a theorem. Okay. So what this says is that if the lateral limits exist, for example, the limit of f of x as x tends to a from the left equals the limit from the right of f of x, and both of them are equal to L, then the limit exists and it's equal to L. So what we are saying here is the limit, there is a limit whenever the lateral limits coincide. Okay, so that's what we need to check. Or in other words, if the lateral limits do not coincide, then there is no limit. We have already seen examples of that. So let's work with the function absolute value of x minus 1. Okay, remember, this is x minus 1 if x is bigger than 1, bigger or equal. 1 minus x if x is less than 1. Okay, so what is the limit of f of x as x tends to 1? Let's see. So let's compute the lateral limits. You see that in this case, the function is a piecewise defined function. And the two halves, they are separated by x equals 1, which is the point where we are taking the limit, okay? So then we are going to compute the lateral limits, see what happens. So the limit when x tends to 1 from the right is the limit x tends to 1 from the right, and then we look at the definition. So on the right of 1, right, f of x equals x minus 1. So that's what we write here, x minus 1. And then the limit is 0, okay? So basically here we are taking numbers that are bigger than 1, but every time closer and closer and closer, but always bigger than 1. Okay, on the other side, when we approach from the left, so in this case, looking at the definition, we need to write 1 minus x. Okay, but again here, so we are taking values of x that are always smaller than 1, but closer and closer and closer. So we are going to get 0. Okay, and notice here, both of them coincide. Okay, so then the limit is equal to 0. Okay, so that's how you do. Now, let's just to complement. So if this here is x equal 1, f of x is going to look like this. Okay, so this is the function x minus 1. You see on the left is 1 minus x. On the right is x minus 1. But then here what we are doing to compute the limit, we are approaching, right? We are following the graph as x goes to 1 from the right and from the left. And you see that in both cases you end up in 0. So it makes sense. Let's do some more examples. So let's do now, this is a very important trick or technique. So let's do this one. The limit as x tends to 1 of the square root of x minus 1 divided by x minus 1. Okay, so Here we already saw in the previous videos that certain problems can arise here. So this is a quotient of functions. So the limit of a quotient is the quotient of the limits. And then these are standard functions. So we can just evaluate x equal to 1. But then what we get is 0 divided by 0, which is an indetermination. Okay, so we need to figure this out. This is undefined. You can say that it's an indetermination or it's undefined. Now, when this happens and we have polynomials, typically we are able to factor the polynomials in some smart way so that we can, so that there is a cancellation. Now, if you notice, the numerator has a square root of x minus 1. The denominator has x instead of square root of x. But x is the square of a square root of x. So we have a square of we have a square minus 1, which is another square. So we can write it. This is what I'm trying to say. The denominator, we can write it as square root of x minus 1 times the square root of x plus 1. Okay, here we are using the property that x minus c times x plus c equals x squared minus c squared. We will use this a lot. Okay, so instead of x, I'm placing a square root of x. Instead of c, I'm placing 1. Okay, but now the advantage is that there is a cancellation. That's why I was doing this. And then there is the limit 1 over square root of x plus 1. But now, before the problem was that it was minus 1, but now it's plus 1. So now we have no problem. When I take the limit of the denominator, I get 2. So this is 1/2. Okay. So here, let's take note of this idea. So this is b. Let's write it with b. Here what I did was writing b is square root of x, c equal 1. Okay. Let's keep this trick in mind at all times. That goes straight to the toolbox. Okay, and then let's do one last example. So let's do something more challenging. So let's take the function that is 3 times x squared minus 5x plus 4 divided by x minus 4 minus x minus 4 divided by square root of x minus 2 times x divided by x plus 4, and that's it. Okay, I'm using square brackets, but they could be round brackets. It's just because it looks nice. Okay, there is no strong reason to do that. So now this is, you see that there is a sum here, well, a difference. Then there is a product. There's a product by the number 3, and then there are quotients. So we can split this limit. This is 3 times the limit as x tends to 4 of x squared minus 5x plus 4 divided by x minus 4 minus the limit as x tends to 4 of x minus 4 divided by square root of x minus 2 times the limit x tends to 4 of x divided by x plus 4. And now we have here 3 limits that we need to compute. But here notice that the first one, when we plug in x equals 4, gives 0 divided by 0, okay? So it's undefined. And then here we have 2 more limits. The second limit, the first limit is problematic because it's 0 divided by 0. The second limit is not problematic because it's 4 divided by 8, so gives 1/2. Okay, so we need to, here what we would typically do, there are two ways to do this. One is you work out the two limits separately and then come back, or you carry everything through and just copy everything line to line. My advice here is that we do the two limits that are involved here. We do them here separately and then come back. Otherwise, we will have to carry everything through, and it's a lot more writing, and it's more likely that we mess up. Okay, so let's work through this. So you see there is a quadratic polynomial in the numerator, 0 divided by 0. So when we plug 4 in the polynomial, we get 0. That means 4 is a root. Okay, so we only need to find the other root, which is 1. Okay, so we factor it out, and then the x minus 4 cancels out, and we are good to go. The limit is 3. Okay, and then for the second, we apply the same trick as before. Did you notice that in the numerator we have x minus 4, x, square root of x? Okay, they are, the x is the square of the square root of x, and 4 is the square of 2. So we can use the trick we were discussing before, this one that is now in our toolbox. Okay, with b equals the square root of x, c equal to 2. So this is square root of x plus 2, square root of x minus 2 divided by square root of x minus 2, which cancel out. The square root of 4 is 2, 2 plus 2 is 4, and we are good to go. So now with this information, let me create some space here. There we go. With this information, we can come back to the main computation, and we have 3 times the result of computing this limit, which is 3, and then the result of computing this limit, which is 4. So 3 times 3 minus 4 times 1/2, this is 9 minus 2, that makes 7. Lucky 7, that's the end of the computation. Okay, something we need to keep in mind from this example is if it's a long computation, it's better to compute. If we see that there are pieces that we can compute separately, do that, because it becomes much easier for us, okay? Then we can just go back to the original computation and plug it in and be done.